Good morning, good afternoon, folks. Thank you for joining today's webinar. I hope at the end you'll gain some value of the end of the presentation, and yeah, look forward to your questions and concerns and so forth. So I will start with the overview of today's agenda, the webinar. I'll give a brief introduction about ETAS, the company that I work for. We will talk about the system on chip, why system on chip, and its contribution to the EE architecture of the vehicle, trends, challenges, evolution, and so forth. And the focus of today's webinar, of course, it's all about security here and security challenges for the automotive SoCs. We'll give some examples, some use case here, and also at the end we will talk about the proposed solution and ETAS proposed solution as well, and some key takeaways at the end of the webinar. Before I proceed with the details of the presentation, I'll just give a brief introduction about myself. My name is Omar Al-Shabibi. I'm the lead product manager for automotive cybersecurity solution at ETAS. I love create value and mutual benefit to our customers and our business. I'm located in Waterloo, Ontario, Canada. It's a city about 15 minutes to the west of Toronto, so we're between Toronto and Michigan. So let's start, talk about ETAS briefly. ETAS co-founded in 1994, headquarters in Germany, basically in Stuttgart. Conceived out of Robert Bosch, and ETAS focuses on it has a wide range of product and services portfolio when it comes into automotive vehicle basic software, tooling, and help realize the software-defined vehicle and enable our customers to have efficient development environment and manufacturing processes and so forth. Script is the security brand of ETAS, focuses on the holistic cybersecurity solution. It's also based out of Germany and has multiple offices globally. Some numbers here for ETAS. We have about 31 locations globally in 12 countries, 23 associates, and growing organization. Now let's deep dive into today's topic, system on chip. I love this topic, because it's really amazing. Why system on chip and the contribution of system on chip to the EE architecture of the vehicle, electronic and electrical architecture evolution. So let's take a simple example here. Everybody's now talking about electrification of the automotive industry. So electrification, autonomous driving, to increase efficiency, of course. ADAS and infotainment systems are the driving factors or the driving emergence of powerful on-vehicle computing platforms. What does that mean? It means you have now more advanced functionality and features within your vehicle, having different level of safety from the ADAS as well as the infotainment systems that are basically driving the high multiple computing platforms you have on your vehicle as an infrastructure to enable these additional functionality that you could have for the OEMs and also for the end user, the consumer and driver of the vehicle. So these powerful SoC platforms are the infrastructure. This is just the terminology I'm using, the infrastructure for the vehicle, right? So this is what if you get approach from bottom up approach, you have a platform. Of course, you need to have powerful software here, and then be able to realize all the different functionality you have on your vehicle. So these powerful SoC platforms definitely are enabling the evolution and transformation of the EE architecture, moving from the traditional ECUs into more centralized domain architecture. It's difficult to realize this type of architecture without really using powerful computing platforms to unleash the potential of advanced feature on your system. So we talk about ADAS, we talk about infotainment systems. Are these drivers for the having system on chip? Of course, you need advanced application layer software and operating systems to enable that thing. But why we need these? All these requirements and infrastructure that we are putting in place, it's going to offer flexibility, value add, to enhance at the end the customer's experience, and increase automation. And at the end, it's all about convenience. So let's just take a simple example. A vehicle year 1980, 1990, vehicle 2022, right? Of course, the achieve the same objective. You drive from point A to point B. You can still achieve that goal. However, the interaction with the vehicle nowadays is completely different than the interaction with the vehicle like 30, 40 years ago, right? Now you can connect your phone using Apple CarPlay, Android Auto operating system environment, and you get the different experience. You have a navigation system, you have different features within the vehicle that added additional safety into your vehicle to provide accidents. Like we talk about blind spot monitoring, we talk about different sensors within the vehicle that aggregate the data and fuse the data and be able to give another perception to the driver to take actions. We have radar, LiDAR cameras, all these type of sensors that are adding the value. They require more computing and powerful brain within the vehicle to achieve what you want to achieve at the end. So that kind of experience and automation now, it's a nice thing. When you drive that type of vehicle and you have these features, it becomes hard to step away from it because it's something now, it's part of your convenience. Of course, there's a contribution for all these different factors we talked about here to something. It's a new term of what we call software-defined vehicle. I'm not going to deep dive into software-defined vehicle today because that's a separate topic and requires maybe a long time to talk about. But I will just use a simple example here, and I think the audience will get this point. Imagine the software-defined vehicle as your phone on wheels. I'll put it that way. Your phone now is your best friend, I would say. You get a lot of updates on your phone, weekly, monthly, whatever. You have all the information, your backend systems, applications, communications, biometric data, all kind of things. So there's a lot of convenience happening here. I can achieve a lot with your phone. So that now the vehicle is moving towards from just not a mechanical and electrical component, but it's actually mechanical, electrical, but also software-enabled vehicle to get the advanced feature of the future. Enabling the software-defined vehicle and realizing this type of advanced solution in the future for the automotive industry does require having a powerful computing SoC. It's a key element that enables this type of technology. Now to move forward, so this is a high-level slide here. It shows the evolution from having distributed all the way to centralized architecture within the vehicle, being able to connect to the cloud and create more like brain in the vehicle, but also other SoCs that could be leveraged within the different architecture of the vehicle to make decisions either locally or push the data into the brain to make decisions. So that update or evolution in the architecture, the electronic architecture of the vehicle, it's enabled by software. Of course, enabled by the SoC, but also software is driving factor of that evolution. That will increase the security threat here, right? So the more you add software into your vehicle, the more you invite many lines of code in your vehicle. You add third parties to your vehicle when they write software. Of course, they have to go through a rigorous process and go through different things because automotive it's highly regulated industry, but it's still the security threat increases here. So we'll talk about this more in depth and shortly. So we talked about the Y system on chip. We touched briefly on the evolution. I would love to make a hypothesis here, right? So and then we drive some analysis on this hypothesis, and of course in a high level, but hope that can help the audience to drive some conclusion. So the hypothesis that I'm introducing at this point in time is of today, system on chip enables advanced functionality compared to a classical microcontroller system. Hence, the security implementation demands a different approach. So microcontroller SoCs, they will coexist. That's, I would say, in the vehicle, right? You need them based on the use case, based on what you need to achieve, functionality, feature, cost, and so forth. Legacy technology probably, right? But the security implementation likely will be different, and we'll explain why this will be different. The use cases remain the same, or they have a lot of similarities here. But the way looking into this needs to have a different mindset and a different way of achieving the final security goal when we talk about complex system. Now let's deep dive into the challenges. I'll start with a problem statement here. Basically, automotive SoC with multiple computing islands and heterogeneous architecture is complex. So the SoC basically is a collection of computers on the same chip. Different CPUs, shared memory, external memory, and each CPU has a certain use case to deal with. So this is the diverse and heterogeneous architecture. We'll give an example in the following slide. Complex automotive SoC have the ability to host powerful software functionality, which increases system vulnerabilities and threats. So the more you write software, as we explained, you're going to put high potential. There's a high risk of having vulnerability in the system. So you have to look after this and consider this in your design when you try to develop a security product in your system. Of course, if what we conclude out of this, the attack surface increases, and potentially the impact of successful attack, of course, is high, right? So it's not like the traditional legacy technology, but this is now advanced technology, have a powerful computing platform, ability to add features as you move forward, right? So when we talked about software-defined vehicle, you release a vehicle today. Next 6 months, you have an update, right? And introduce a new feature to the driver, or you do upselling for the OEMs, when they want to do, changing the entire business model, to be honest. But that needs to be consider the security in it. So these are the kind of the problem statements we try to address in today's discussion. So let's take an example. When we say complex architecture or heterogeneous architecture, what does that mean? Let's just touch base on this in a high level, right? Security is a SoC wide integral concern. Means you need to have a secure environment right from the beginning. And if we take an example of this, secure boot is a good example of that one. Security is not just one-time thing, and it's not just one subsystem of the entire SoC. No, it's for the entire SoC, the entire ECU, and the entire system. Security spans multiple computing nodes within the system. So you can see this is the high-level diagram here. So this is not a comprehensive diagram by all means, but it's just a diagram. We're trying to simplify the picture as much as possible, but by conveying the complexity in a simple story. You have multiple real-time hosts here. I don't know, 6, 8 cores, whatever, depends on your design. You have multiple application cores here. We talk about probably A72, whatever ARM family, product family that you introduced based on the silicon supply. Multiple channels, multiple DSPs, multiple GPIOs, connectivity, wireless module, multiple hardware accelerator, right? So this type of technology, when we talk about HSM as well, HSM core, right? Multiple HSM cores, right? Like a dual, let's say dual HSM core possibility, maybe even more than dual HSM cores, right? With the hardware accelerators. This did not exist in the classical microcontroller, period. And we have, this is, not the traditional way of achieving your security goals. There are significant differences in the SoC architecture in the lower level. When we talk about the interconnection, the hardware abstraction, partitioning of your hardware, access control, several aspects that you have to look into, right? How the R5F or whatever real-time hosts communicate with the HSM and so forth, hardware accelerators, which one you access, how you deal with it. So that level of abstraction, it may differ from one SoC to other SoC supplier. Even with the same silicon supplier, you may have different product families and different variants that could have different interconnections and different architecture that you need to look after. So this is kind of the complexity we're talking about here. If we pick an example of a security use case related to the performance, and this is kind of the topic that we want to touch base on today, how you, in addition to the challenges that we talked about, complex security, but how you retain and maintain high-performing system while you have security, integrity, and robustness in your system. So the in-vehicle communication requires high bandwidth. Of course, we talked about having multiple sensors within the vehicle. You have radar, LiDAR, right? You have cameras. We talk about gigabit Ethernet traffic. And the key message here is the higher the bandwidth, the higher demand on security operations. So there's a correlation here, and there's a linear relationship. The more you add bandwidth, the more data you have to secure and look after. The demand on security operation will go high. Security requirements. This is a 200,000 feet view on security requirement, because if we want to deep dive into security requirements, we may need to spend hours and probably days. In-vehicle communication requires security to ensure authenticity and data integrity. Obviously, secure communication deals with different protocols: CAN, LIN, FlexRay, Ethernet. Secure communication requires high-performing functionality, because we are sending, receiving, and you have to look after that type of performance and transaction per second, throughput, and so forth. And ideally, security use cases should have minimal impact on system resources and utilization. You don't want to have a high secure system and lose on performance, and vice versa. You don't want to have a high performing system and lose on security. So you have to have an intelligent, creative way of achieving these goals from a security perspective. From the initial design analysis, we could tell that overhead of security is real, something that must be considered in the design, architecture, implementation of security libraries, security product, and so forth. And definitely influenced by the platform capabilities. We talked about, from one silicon to another silicon supplier, different architecture, and that's the challenge that we are dealing with. There might be some bottlenecks, some within channels within the SOC, bottlenecks, multiple CPUs, multiple cores try to access the hardware security module to perform some specific crypto operations, and that, challenge here. That we have to consider, basically. So we talked about the use case, we talked about the data here. Radar is a good example, right? We talk about ability of processing data whether locally, or you send the data to the vehicle computer or brain to process the data at that central unit. Depends on your design and what the OEM wants to achieve, but that's something from security perspective needs to look after. So in addition to what we talked about the security of SOC, I want to also tie this back into the ECU level security here. Of course, there's a bigger level even than ECU, which is the entire vehicle, entire system, but we're not going that route because it's even complex and requires more time. But with this simple statement, system level security is fundamental aspect and needs to be considered at the beginning and throughout the ECU lifecycle. One simple message I want to put forward here: security is not a one-time event. It's not design it, implement it, deploy it, and be done. No, you have, because the more ability of software you're developing, testing, deploying, you need to consider that the entire security ecosystem is bulletproof, and it's helping assessing the risk and not jeopardizing and putting your fleet, your vehicle, your entire system at risk. So that kind of thing, it's something that always needs to be in the mind, which I think it's already in the mind of a lot of automotive players here. We talked about the challenges, we talked about these things. So here's just more of like a recap-ish kind of thing. Increasing the risk as a challenge of cybersecurity attacks and unauthorized access. So that's definitely, it's not shrinking. We're not trying to scare everybody here, but it's fact. We have to do, we have to live with it, right? It's a truth. You want to have more features, you want to have advanced functionality, and you want to have different experience to bring to your drivers. You try to revamp your business model for the OEMs and so forth. This comes at cost and consideration right from the beginning that you need to consider. The needs for that one is you need to have a smart SOC zero trust security platform through defense in depth mechanism, and having this robust system enhanced with the performance requirement. And this is important here. And having this kind of defense in depth mechanism, when we talk about the firewall in your system, the HSM, trust zone environment, hypervisor, so isolation of activities and tasks and so forth. Now, we talked about the challenges, we talked about the evolution, we talked about, possibility of potential risks of, security challenges and attacks. Let's talk about proposed solution for this. So what is the proposed solution here? This start right from the beginning on the design level, right? So this is not something that you want to design your system and then assume, oh, it's secure, or I can add security later on. It will be too expensive. It will take a long time. It will impact your cost, your business model, your setup, and everything else. So what we are proposing here is a parallelization of security tasks. Instead of funneling everything on one task, one channel, one path, you have to dissect this and introduce multiple paths in this. That yields into a as an outcome, decentralization of security components. The decentralization of security components is like the modular approach. Will definitely put you in a position to have a modular, performant, and secure environment. So this is kind of the design strategy. Meaning is, when we showed the example of multiple computing islands on the system on chip, you don't want to look into having a secure solution. Yeah, I have an HSM and that's it, done. It's not. Looking at the different aspects of your system, what you're trying to achieve. Security use cases remain similar, but the way that you're trying to implement and achieve the security goals and the security use cases, such as secure communication, secure boot, diagnostics, so forth, needs to be in a different mindset. Having parallelization, creating different security libraries, security components to create a modular system to maintain performant environment while security is not compromised. So this is kind of the design strategy we are proposing here. This is what we think, could basically alleviate the concerns or eliminate these problems at some point in time when it comes into high-performing, complex, diverse architecture. So with that introduction of a proposed solution, I would love to talk about what ETAS is doing. ETAS definitely recognizes the SOC security challenges, and now introducing a new solution that hopefully fixes the challenges and create value to tier ones and OEMs at the same time. So ETAS is introducing a new product called Cycler SOC. This means Cycler stands for Cybersecurity System on Chip product. It's we call the de facto standard for microprocessor-based system on chip. It's an embedded cybersecurity solution, software solution for the HSM firmware, plus the real-time host domain and system of the system on chip, and host domain of the system on chip. We'll talk about this shortly in the next slide to give some context into what we talk about here. So Cycler SOC provides all security functionality for the SOC platform and enables all these security use cases: secure boot, communication, production, so forth. Implementing all these security use cases, you need to have the entire system that has the ability to perform all these things. The product will provide the cryptographic operations protocol and ensure that whatever ask and request comes from these different use cases, different SOCs, different ECUs being done properly and with integrity in mind. It does establish root of trust, enable system authenticity and integrity, and help fulfill the complex automotive OEM security requirements while ensuring smooth integration, because this is a challenge here. Integration is not trivial, but that's, we're trying to create an abstracted product, and we'll talk about this shortly, to retain integrity, functionality, and achieve reliability and safety of your data and your contents. This is the high-level diagram of what we envision Cycler SOC. Cycler SOC, what we call family of different variants, has the vision to have building blocks, creating some sort of a marketplace here with building blocks. Of course, the core of this is going to be the HSM firmware, but it's not only going to be the HSM firmware, but rather leverage the resources within the complex SOC environment to add additional security functionality and secure these sub systems or assets within your entire system. We talked about the complex SOC. We showed the subsystems within the entire system. Each subsystem has, ability to achieve certain security goals and objectives, right? So we talk about the A72, we talk about the trust zone environment, and this could be another, it's what we're trying to envision, it's another variant of CyclerSOC product to leverage the trust zone environment and provide cryptographic operation and help achieve security goal with high performance on this application environment. Of course, does require integration on VM side. We talk about the hypervisor and POSIX operating systems. So this is more of the high level components of the CyclerSOC product. You might end up with a use cases and application where you have the TEE version of CyclerSOC and the HSM version coexist, depends on the use case, or they could be separate. It depends on how the OEM proceed on their security implementation. So this is kind of the nutshell of the product. This is what we believe, addressing the complexity of SOCs, enabling the security environment for the complex software application and so forth. Why you need to work with us and why we add value here. We understand the problem, we talked about it, increasing system vulnerability and threats. We're creating an environment where it's actually modular and flexible from an HSM core as an HSM firmware to a dedicated core while maintaining high performance, security, integrity, robustness, and zero trust concept. And creating an abstracted solution from the OEM requirement and from the underlying silicon diverse and heterogeneous architecture to be able to help the OEM save on cost at the end of the day. That's the goal, and this is what we are designing. This is what we're working on to create that scalable, portable, and configurable solution. So proceed on the summary here of the deck of the webinar. Why automotive OEMs care about security, and they do care about security. We're trying to be consistent on the message and repeat that thing. Connected. We talk about autonomous connected vehicle, right? Have contents that need to be controlled and secured properly. Ensure integrity of data and system authenticity. Achieve reliability, safety, data protection. And to protect the public and the assets. This is important here. Ensure cybersecurity lifecycle management is in place, and this is very, very critical task. Security is not a one-time transaction. It's not a one-time event. It's a continuous operation. It's a continuous monitoring to give the OEMs, tier one suppliers, and any supplier for the automotive industry to have better visibility on risk management or risk assessment. With that, I conclude with some key takeaways to be consistent on the message, repeat the same message here on automotive SOC and advanced software functionality, increased system vulnerability and threats. As we talked about, security is an evolving mandate that needs to be considered at the onset and throughout the vehicle lifecycle. Remember, it's not a one-time event. Flexible scaling security solution addresses the heterogeneous SOC architecture, the diverse architecture, multiple subsystems, multiple CPUs in the same environment. You can have multiple SOCs on the same ECU. Securing an SOC is complex, period, and requires a specialized in-depth security knowledge and a team that could achieve your security goals in a cost-effective and efficient manner. With that, I conclude today's webinar. Thank you for listening. I hope I added value to you today. Thank you.